Hello, everyone. Welcome to the CITRIS Research Exchange. I am Professor Ming Wu. I'm a faculty member at the EECS here. I'm also chief scientist at CITRIS, and it's a pleasure for me today here to introduce our speaker today. Before I introduce her, I'd like to thank Infineon for sponsoring the research exchange and for providing the lunches for all attendants. Also, I'd like to welcome viewers, web viewers from our three sister campuses, UC Davis, UC Santa Cruz, and UC Merced. And hopefully you can all see us and hear us right now. And also, I'd like to remind you a few future events we have. You are all welcome to our holiday and spatial theater performance on December 12th at 4 p.m. And also, I'd like to mention a few upcoming distinguished speakers in the next couple of weeks. On December 5th, we have Danish ambassador here to speak at 2 p.m. in Sibley Auditorium. The subject of his speech is the EU as a rising superpower. I'm sure you're all interested in the subject. And the following Monday, December 8th, at 4 p.m., we have Dan Sperling, who's the director of Institute of Transportation Studies at UC Davis. He's going to talk about 2 billion cars and California climate policy. So these are all very exciting events. Today, it's a pleasure to introduce our speaker, Dr. Cecilia Aragon. She's a staff scientist at the Computational Research Division at the Lawrence Berkeley National Lab. Her research interest includes visualization and analytics of large scientific data sets. She has an amazing career. She receives her bachelor degree from Caltech and taught herself to fly. She's a professional pilot for helicopters, and she can do all kinds of difficult maneuvers. I just thought Peter Abil, our new faculty, would be thrilled to interact with her. Among all her very busy schedule, she managed to found and serve as a CEO of a company, Top Flight Aviation, which combines her expertise in flight control and computer science. And after that, she came to Berkeley, became a graduate student in the computer science division, and received her degree in 2004. In between those times, she also took a leave from the company and worked at NASA Ames Research Center, and then joined LBNL. So today, she's going to talk about facilitating scientific insights with Sunfall. That's the software that she has developed. Okay, let's give Dr. Aragon a warm welcome.
Thank you very much, Ming, and I'm very glad to be here. It's always a pleasure to come back to the UC Berkeley campus and see old friends and see the campus again. So I'm going to talk about let's see. I don't know whether the slides have swapped out. Okay, there we go. All right, so I want to start out by talking about Berkeley Lab a little bit, because I found that oftentimes people here on campus aren't that familiar with Berkeley Lab, and that's a shame, because we're, with the CSE program that's being developed, we're hoping to foster closer ties between Computational Research Division and faculty in many divisions and students in many divisions down here on campus. So I want to talk about the kind of research we do at the lab and how we facilitate scientific insight. I'll give a very brief background of the particular astrophysics problem that we're trying to solve, and then I'm going to describe the project, the Nearby Supernova Factory, where I was developing, that I was a collaboration member of, where I was developing software. I'll describe the software framework we developed called Sunfall. And then I'm going to talk just to give a brief overview of the rather wide range of computer science research that resulted from the Sunfall development. And finally, conclude with some lessons learned. All right, so if anybody doesn't know, the Berkeley Lab is just up the hill from the campus. We're a shuttle bus right away. You know, if you're a student, your student ID will get you on the shuttle bus and you can come up and visit us. The mission of the lab is to solve the most pressing and profound scientific problems facing humanity. So just so that people know, we do not do any classified or weapons research. It's all unclassified research. We're trying to discover new materials for alternative energy, come up with solutions to alleviate climate change, understanding living systems. We have a large life sciences department to improve the environment and the energy supply, and to understand matter and energy in the universe. So we're solving basic physics problems, as well as problems that impact all of us here on this planet. We also want to operate scientific facilities that are in general use for the country, such as NERSC, the National Energy Supercomputing Research Center, that provides supercomputing compute power basically to anybody. Anybody can apply for time on the supercomputers. And finally, we want to train the next generation of scientists and engineers. So we have programs for students ranging from high school through graduate school. We have many postdocs at the at the lab, and we have an active outreach program. So we have just under about 4,000 permanent staff, of which a large fraction are associated with the university. We have faculty, postdocs, grad students, and undergrads. And then we have about the same number of guests each year. So that brings us to a total of about 7,000. Okay, so I'm in the Computational Research Division. And our job is to collaborate with scientists to develop the computational tools and techniques that can facilitate scientific experimentation, also computational modeling and simulation, and that can lead to new understanding in these areas listed here. So what I particularly work in are the astrophysics experiments. So that's what I'm going to talk about later on in this talk. But there are people working in each of these areas closely with scientists. All right, so NERSC, as I said, serves the entire scientific community. We have about 3,000 users, about 400 projects, and the focus really is on large-scale supercomputing and parallel computing. And as I said before, anybody, students can apply for time. You don't even have to be associated with a university. Individuals and companies, members of companies, if they're interested in doing scientific research that requires supercomputing, they're welcome to apply. Although it is a very competitive process. But I invite you to visit nersc.gov and find out more about the Supercomputing Center. All right, so I'm working in applied computer science research. And so I want to talk some about why I find that so compelling, why I chose to do this over working in pure computer science research. Well, first of all, I found that real-world problems really lead to some very interesting research questions. It just seems that the problems just arise naturally. And one person described it as the problems just come flying at you. And so it's very easy to choose a research problem where you can have a substantial impact. So if you can solve this problem, it's not just that that you've published a paper and you've done great creative work, but in addition, you have impact on the world around you. So I'd like to also mention at this time that at Berkeley Lab we do quite a bit of this type of research, and we are actively involved in collaborations with universities and companies and other labs around the country and around the world, and we welcome students and faculty members to come and collaborate with us. We have summer students at all levels, as I said, from high school, undergrads, and grad students, and we have some wonderful postdoctoral fellowship programs, such as the Alvarez Fellowship, which is open right now. And so please, if you're at any of these stages and you're interested, visit our website at lbl.gov. All right, so what are some of the problems facing us in scientific research today? Well, one of the major problems that we're facing is an overwhelming flood of data. And this has been known as it's been called the data tsunami. It used to be, really not too long ago, but 15, 20 years ago, scientists would run a simulation or they would conduct an experiment. They would gather a bunch of data and they would store it on disk, and then they would take it home, study it for months, process it manually, use that to come up with scientific insight. However, that has been changing. In the year 2000, the data generation rate for the first time exceeded the data retrieval rate. What that meant is that people are now writing more data than they are reading. All right? So, in other words, scientists don't have enough time, really, to process all the data. So, part of what our mission is to try to make this problem a little bit easier. How can we make it easier for scientists to process this huge amount of data? So, it's the Department of Energy, which funds Berkeley Lab, has called this at one point the Petascale challenge, and referring to petabytes of data. At some point, of course, this is going to be obsolete because we're going to have much more than petabytes of data. But it has generally been shown by looking at various data points, the amount of data in the world is increasing exponentially. Actually, we already have exabytes of data in the world, and that was, I think, a few years ago the last time I saw a study on it. So, what do we need in order? What's the rate-limiting step in this problem? How can we understand data? Well, we all know that we need to build faster computers. We need to build more parallel computers. We need to develop new software that can run on the parallel computers. So we need to work really hard. But if we do it, it looks, thanks to Moore's law and human intellect, it looks like we can maybe keep up with it if we work very hard. So, what about human cognitive capacity? We're not evolving at the same rate that the hardware is. You can say maybe that we're getting a little bit better because students now can text and listen to lectures at the same time. So maybe the multitasking capability has increased a little bit, but really, at best, it's linear. All right. So, how can we, we have this gap, and how can we approach this and try to solve it? So, some of the issues that we have been looking at Berkeley Lab, all right, are these are methods of fostering scientific insight. Okay, so one person maybe can't deal with all this data and can't deal with understanding it, but what about interdisciplinary teams? Get a bunch of really smart people together. Each of them has years of scientific training in their particular area. Get them all to work together. Well, that has been a very promising approach. There are some difficulties, though. Whenever you have a distributed collaboration, people in different institutions, people with different vocabularies, there are a number of challenges that need to be addressed. And so part of what we are working on are tools to make this type of collaboration easier. A recent study by the National Science Foundation studied about 500 interdisciplinary scientific collaborations. And what they found is that people tend not to work together. Even in so-called interdisciplinary collaborations, what you often have is the people in this institution are working together and the people in this institution are working together. They just split the money. They don't often really work together on a daily basis. So what can we do to change that? This is something that I'm going to talk about one example of a distributed collaboration where it was actually successful, and I'll talk about some of the tools we built in order to facilitate this process. So I'm suggesting that I think we need to look at this process in terms of scientist-computer interaction. Just like there's a disciplinary field human-computer interaction, I think we also need to study how do scientists interact with computers. We know that scientists use computers in ways that are different from the general population, and many ways that are the same. So how can we focus on some of the commonalities and facilitate the scientists and their ability to solve these very difficult problems? All right, so now I'm going to shift gears and focus in on the science background. I'm going to talk a little bit about astrophysics. So about 100 years ago, Einstein was developing his theory of general relativity. And as he did, he wondered, why doesn't gravity cause the universe to collapse? You have all these objects in the universe. Why aren't they just all smushed together? So in order to make his mathematical equations come out right, he postulated the existence of a cosmological constant, lambda, which sort of acted as a force that held the universe apart. So then just a few years later, Hubble discovered that through observing galaxies that the universe was actually expanding. And so there was no need for lambda. And Einstein called the cosmological constant at this point his greatest blunder. So the next question then is, okay, so we imagine there's a big bang, the universe is expanding. Well, will the universe ever contract? I mean, it must, because eventually gravity will force, will act to counteract this explosive force, and everything will, presumably come back into a point. Okay, so we need to measure the deceleration rate. And so there were a number of groups working on this for many years. And then about 10 years ago, 2 separate groups with principal investigators at the lab and also here at UC Berkeley, as well as physicists at many other institutions throughout the country, studied supernovae, exploding stars. But there's a particular type of supernova that can be used as what they call a standard candle. It's essentially, it looks about the same wherever it appears in the universe. I'm really oversimplifying here, but we don't have time to teach all of astrophysics in about 10 minutes. So what they discovered was this really astounding discovery that was the science called the breakthrough of the year in 1998, is that instead of slowing down, the rate of expansion of the universe is actually accelerating. All right? So it's actually getting faster and faster. Okay, so this type of supernova that they used to study this is called a type 1a supernova. And what makes it very interesting is that it is postulated. We don't know this for sure since these supernovae have all been very distant. It's postulated that these are binary star systems where the solar material accretes onto a white dwarf, and when it reaches a particular mass called the Chandrasekhar mass, which is about 1.4 solar masses, certain conditions are right for a thermonuclear runaway, an explosion essentially. And at this point, you see the supernova, bright in the sky. All right. So the type 1a supernovae are very interesting because they do have this, since they all explode presumably at about the same mass, they have a lot of characteristics that make them similar. However, there are challenges if we want to study them and use them as cosmological distance indicators. First of all, they're really rare. A typical galaxy like ours, the Milky Way, which has about 400 billion stars, will only have 1 or 2 of these in a millennium, in 1,000 years. All right, so, and we want to study a bunch of these. And they're random. So, if we want to point our telescope, we don't know where to go, all right? And finally, and they're fleeting. They reach their peak brightness within only a couple of weeks, and we get the maximum scientific benefit if we can study them as they're getting brighter on their way up to peak. Okay, so this is a big challenge. So the basic idea was let's take a wide field search of the sky. Let's take many images of the sky, and we'll statistically predict the number of supernovae that will appear in this area of the sky that we will predict, so that we'll find them on a fairly quickly, so that we can get a bunch of them together and study them, and then schedule the telescope time afterwards to identify to follow up with spectroscopic study. Yes?
Why does predicting the number help you actually see it?
Well, it's just because it tells you how much of the sky you need to study in particular. That's all. It also gives the supernova rates. It also gives you an idea of you can tell how good your algorithms are as well. Okay. So they found using this technique with a data set of only about 80 or 90 type 1a supernovae. The 2 separate groups made this prediction, which has since been confirmed using other methods, that the universe is expanding at the accelerating rate. So the big question is why? What is going on here? So at this point now, if you look at the equations of state of the universe, it looks like dark energy is about 2/3 of the matter-energy budget of our entire universe. All right, so 2/3 of everything around us, and we have no clue of what it is. So this is a really exciting time to be a physicist, to be an astrophysicist or a cosmologist, because it is generally believed that in order to understand dark energy, as we do gather more data, may usher in a revolution in our understanding of fundamental physics. And so learning more about dark energy is really one of the most fundamental problems in physical science facing us today. So in order to answer these questions, what we really need is more data. You know, a data set of only 100 supernovae isn't really enough to put tight limits on some of these cosmological equations of state. So what this is here is the Supernova Legacy Survey, SNLS, is a large data set of different supernovae. And this is what by studying some of the data there, this is where the original discovery was made. The Supernova Factory, which studies a set of nearby supernovae, is going to narrow the limits on the equation of state. Okay, so what do we have to do in order to get this? Well, the Nearby Supernova Factory is the largest data volume supernova search currently in existence. So the goal is to find one of these type 1a supernovae every night. All right, and it was about a 3-year project. So one of the questions I'm often asked is, well, you say Nearby Supernova Factory. How nearby is nearby? Well, you know, astrophysicists have a different time scale than the rest of us. The range that we're looking at is of the order of 1 billion light years away. And that's considered a nearby supernova. And what you do is, the reason it's nearby is you compare it with the universe is estimated to be about 14.7 billion years old. So if you're looking at supernovae around 10 billion light years away, those would be what they call high Z or high redshift supernovae. We're looking at this one particular area for particular physics reasons that I don't want to get into today. So here's our collaboration list. There's about 30 members in 3 institutions in the US, Berkeley Lab, Chicago, and Yale, and also 3 institutions in France. So we are an interdisciplinary, multi-institution, international collaboration. A quick overview of our supernova search data flow. So the Near-Earth Asteroid Survey does wide field imaging of the sky every night on the Ocean 1.2 meter telescope in Mount Palomar. So that's a separate project. We piggyback on that, and we get all their data. It's sent over to NERSC, where our custom image processing algorithms, you know, run in parallel overnight on the supercomputer. It's about 30,000 images, which is about 50 to 80 gigabytes of data every night. Okay, this is why it's called a factory, okay? Because we have to process this huge amount of data every night, and it has to be ready by the next day so that people can look at the data and analyze it. What this is over here is, what we do, essentially, is there's a reference image of the sky that was taken weeks or years ago, all right? So you just have a bunch of stars in the image. Then you have the current image, which might have a new bright spot, okay? So here's a reference image. It's just a snippet. The images are much, much larger than this, but we've just snipped out one piece. So this is a galaxy that's in the original reference image taken maybe 3 weeks ago. Now this was today's or tonight's image, and you see there's a little bright spot over there? Well, that's a potential supernova. And then you do an image subtraction, and you end up with a bright spot. That could be a supernova. So what you do is you get the coordinates, the sky coordinates of that object, and then you send the coordinates to another telescope on the top of Mauna Kea, the University of Hawaii 2.2 meter telescope, where there's a dedicated spectrograph that was built just for the Nearby Supernova Factory. We call it SNFS, for Supernova Integral Field Spectrograph. All right, so there are a lot of difficulties with processing this data set. First, I showed you there's these beautiful Hubble telescope images of galaxies and supernovae. You see how bright they are. They're almost as bright as the galaxy itself. And you think, well, hopefully we get images that are that beautiful. Well, not really. Okay, we're still in the atmosphere. The CCDs are maybe not of the highest quality. So there's issues. We have this fringing, lines that come across the images. There's reflections. There's saturation on the CCDs. Dead pixels, cosmic rays in airplanes cause problems. So what we have to do is subtract images that may look this different from one another. And we have to somehow take out all these artifacts so that we can get nice, clean, subtractions that show us where the new bright dots, which are new transient objects in the sky, and hopefully new supernovae. All right, so when I first joined the project in 2005, they had the project was in place, they had received funding, they had telescope time, and they had a number of the basic algorithms for doing the image subtraction in place. But they were having a lot of problems. And a lot of this had to do with the fact that their algorithms had some issues, and there were also just problems with, this goes back to, there were problems with getting the scientific data from one tool to the next. Some of their tools did not scale, I'm sorry. So I'll go through more of these pieces in detail later. But the essential part here is that although they had little pieces in there, they had no tools for data exploration. They had to do there was a lot of human intervention that really wasn't required. They would get an email with a bunch of long file names, and they'd have to cut and paste those into the next program. Just was a waste of a lot of smart people's time. So our job was to develop this software framework for the Supernova Factory. And so Greg Aldering, the principal investigator of the Supernova Factory, was, I think very visionary in that he realized that you need an interdisciplinary collaboration in order to solve this problem. So in the old days, astrophysicists used to say, oh, if I have a computing problem, I'll hire one grad student, and they can solve it, right? But now with, we have these large projects that require a great deal of computational insight, really. So you need computer scientists, people with expertise in various computational techniques, as well as the physicists with their expertise in the domain. And what you really have to do is you have to work very closely together. We attended the scientific meetings, whether they were by video conference or in person. We ate lunch together when we could. We attended the collaboration meetings. And we also participated on the electronic means of communication, which we used the chat room very heavily. Another thing that was very important is we had a single funding source. I think this is my personal belief, that if for interdisciplinary collaborations to be successful, you really need that single funding source, because otherwise you'll have two groups, each of which has to please a different master. So these are just some of the areas of expertise that we brought in to work on this particular problem. Human-computer interaction, situation awareness, which is a technique that I learned about through my work in aviation. It just means being aware of the world around you, knowing how to predict where things are going to, from aviation, it's how can you predict where another airplane is going to be in a few minutes, right? How can you predict where you are going to be? Machine learning techniques, very important in processing large amounts of data for physicists. This is becoming more and more active in just about every scientific problem. Image processing, of course, because we're dealing with image processing. And finally, scientific data management. How do you deal with moving these very large amounts of data from heterogeneous sources and marshaling it all onto a place where the scientists can access it? So these are the main software framework contributors. And I put this list up partly to show what a range of expertise there was here, that we had people working. We had software engineers, we had computer scientists in many different areas, and we had physicists, and we all worked together on this project. It wasn't just, the physicists work here and the computer scientists work here and they share information. We worked together. The scientists developed software. We as computer scientists learned about physics. So what we developed was what we called Sunfall, or the Supernova Factory assembly line. And so this is a software framework that handles the supernova search and data analysis and processes it. And it's also a tool for scientific discovery and workflow visualization. So there are four major parts to the framework. First of all, the search, which I've been talking about. This is the high-volume image data pipeline. I'm going to talk about each of these in a little bit more detail later on, but I just want to give the overview right now. The workflow status monitor, which is essentially a web-based dashboard which helps give these scientists situation awareness, so they know where all the data is in the pipeline. They know what's going on. If one of the nodes, if the supercomputer goes down, they know what's going on and they can act to process it right away. The Data Forklift is a tool for scientific data management. It's specifically designed to to gather data from that's hosted on computers not under the Supernova Factory's control, that might be in heterogeneous forms. It might be like there's one very slow website where the scientists need to get asteroid data. And what it does, so all of that is processed and marshaled on the Supernova Factory servers so that it's available for data exploration the next morning. Finally, the Supernova Warehouse is the tool that we developed for interactive data exploration. So the search, what we did there is we incorporated legacy software and we improved and added new algorithms to it. And all the other three parts that we wrote from scratch. So this is just an overview of what the Supernova Factory data pipeline looks like today. The blue areas are the legacy code, and then the yellow is the new code that was added onto it. And the main thing I want to point out here is that a lot of the data transfer is handled by the Data Forklift. There's much less need for human intervention, although there still are some critical areas where humans are needed, where there are things that humans can do better than computers still. And so we rely on that. So now what I'm going to do is talk briefly about the architecture of Sunfall and some of the major pieces. And then I'm going to spend some time going through an overview of some of the computer science research that came out of developing this software tool. So what we did is we both built a production software tool that the astrophysicists are still using today, or even though we've moved off the project. But we also had original computer science research in a number of fields. And this, again, I said, is one of the great parts about working in applied research. You get these ready-made problems where you can really have an impact, and you have a fun problem to work on, but you do also get publishable work in peer-reviewed conferences in computer science and also computer science journals. So this is a web-based dashboard that shows the status of the Supernova Factory data. All right? And essentially, the important part to see here is that in a single page, what it does is it gathers all the information that a scientist who's operating this pipeline needs to know if something goes wrong. If anybody here has worked on a scientific workflow system, and one of the big problems in scientific workflow research now is how do you deal with error detection and recovery? It's not an easy problem, all right? And so given, often one of the best ways is to, again, rely on a human to detect some of these critical error stages and fix it properly. All right, so we streamline as much of the workflow as we can, and then we present the information to the humans so they can make a quick decision. Okay, so the data forklift. The problem we have is we have this tremendous amount of heterogeneous data that has to be processed, moved around, queried, and displayed. All right, so as I said, we have the large amount of image data, but there's also quite a bit of metadata that is generated as the pipeline moves along. So the Data Forklift is a suite of services for doing automated data storage and retrieval and staging for display. All right, so here is where they run on a central location from the Supernova Factory server, and they're secure because although supernova data, scientific data is not, isn't subject to the same restrictions that, say, commercial data is, nevertheless, scientists don't want to be scooped, all right? Their careers may rest on it. And there was a famous situation in astrophysics where some of the people who discovered, what the 10th planet or what they thought might be the 10th planet, they made a mistake and made that data, those image data, available on the web, and somebody did some careful sleuthing, found out the coordinates of that data, and were able to announce, the discovery of this planet ahead of this other group. And so it's not quite clear what happened there, but the point is that now the astrophysicists really want their data to be secure. So the forklift has to be reliable, self-restarting, and as I said before, fault-tolerant. That's really critical. Okay, so the Supernova Warehouse is a tool we built using participatory and iterative design, working with the scientists. How do you need to see your scientific data, right? And so this has a number of features that I'm just going to go through very briefly. This image up here in the upper left-hand corner is it's a two-dimensional map of the sky. It enables scientists to easily predict what objects are going to be doing over the course of the night when they're at the telescope. It's set up so the objects just move linearly from left to right. And these curved lines here that blue one is the horizon. And you can also see where the moon is, although I don't know if you can tell at this point. The moon and the sun are also visible there as well. All right. So we also produced, this is another part of the Supernova Warehouse. I'm going to talk about this in particular. In order to take data at the Summit telescope, they need to see, they point the spectrograph at a particular site, and then they want to see where, what the data is like. So this is the spectrum here, and these are all in the visible, in case you're interested. And what these little, we call them postage stamps are, is one of the problems they found out when the scientists first started doing this. You have to run the telescope late at night, obviously, right? So you have this geographically distributed collaboration, operating the telescope over many different time zones. And so everybody in the collaboration has to participate. You often have people who are novices at operating a telescope. And so there were some errors where this expensive telescope time was being wasted, where people were pointing the spectrograph at the wrong coordinates, right? And so, a very simple visualization like this shows you where you're pointed, so you can see where the spectrograph is pointed, and also it helps evaluate the quality afterwards, the quality of the spectrum. For example, when the scientists are looking at this particular supernova, when they're studying it after the fact, they can see that this is a good quality spectrum, partly because of, you can see that the supernova is relatively well centered in the target frame here. But over here, you just got a bunch of junk on the blue spectrum. And this one here had a few problems too. So you can see that your spectrum is not as high quality. And here's another one where there's some problems. So that's sort of a marginal one. And then you have a good one up on top. So this relates again to situation awareness. In aviation, what you see is that you need to make decisions very quickly. And there's some surprising commonalities with supernova science, because as it turns out, as they're observing these spectra on a very time-limited fashion, they have to make a decision in as little as 45 seconds. So you have a novice dealing with this very complex telescope interface. They're operating it remotely. They don't have the normal cues of when sunrise is coming up. And they have to make a lot of pretty sophisticated decisions in a very, very short amount of time. So you need to provide them with tools that are in some ways similar to the tools provided to pilots today to assist them in making challenging decisions, dealing with very large amounts of dynamic data in a very short time. All right, so now I'm going to talk about some of the research. Now, I'm going to have to go through this very quickly. We do have papers on all of these areas, so I'd like to encourage you to, I'll give you my website at the end, and we have papers on all of these if you have more questions, or you can stay afterwards and ask me about them. But essentially, we've generated quite a bit of research results in machine learning, in image processing, human-computer interaction, visualization, scientific data management, operations research, and astrophysics during the 2.5-year course of this project. So, some of the first research work that we did on this project is we applied machine learning in a. The reason I'm hesitating is I could talk for an hour about this project. So I'm just going to say very briefly that we applied machine learning to the Supernova Search project, and so the search, as I said, piggybacks on that one telescope. We have this huge amount of image data, and then we have the reference images and then the new images. And what we do is we generate about 20 features from each of the sub-images, and then in the past, what they just did is they had cuts. They had minimum and maximum values. Right? This is, you have a grad student working in physics working on the problem. This seems like a logical way to do it, right? But the problem is it's a 20-dimensional search space. all right, and you have this rectilinear box, obviously it's not very efficient. You're going to get a lot of false positives in your result set. So essentially, we applied support vector machines and then boosted decision trees in order to reduce the number of images that had to be scanned every day from 1,000 down to 100. Okay, so also when we were looking at the subtraction pipeline, we looked at the image processing of the particular data, and we discovered that there were issues. Sometimes their software was passing images that looked like this, which were that's clearly not a supernova. It's clearly a misregistration and an error in these two stars that ends up with that. Whereas you have a real supernova would look more like the top image. So one of the tools we came up with is let's analyze the shape of this potential supernova by using Fourier contour descriptors. And when the idea was first proposed, the physicists actually didn't think it was a good idea, because as soon as you say Fourier, they say, oh, it'll take too much computation time. All right, so we actually developed a linear Fourier contour descriptor technique, which actually it's really constant time, because the contours are never going to be more than about 40 pixels, so it's actually very small. So we called them roundness and wiggliness. All right, so you can just take the ratio of the powers in the lowest order negative and positive Fourier contour descriptor sequence, and that gives you an idea of the eccentricity of the object. And then the wiggliness is really the amount of energy in the contour. All right, you take the power in the higher order of Fourier contour descriptors divided by the total power. And we do it fast because we pre-compute. You know, it's a Fourier transform, right? It's a Fourier transform of complex numbers, and you can preload them in a lookup table and just do integer math and just have have a pointer into the table, and this can work very, 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 very rapidly. So as a matter of fact, we put it in the test, of course, is we inserted it into the system, and we did a time test on it, and we found out that it was the amount of time that was added by this new algorithm was negligible, but it reduced the number of bad images by 70%. So again, a significant improvement in the data, in the quality of the data. Then there are some simpler things that we did. For example, as I mentioned before, they were cutting and pasting these emails from one side to another. We simply developed some improved user interfaces, and what this did is it used to take a scientist about 2 minutes per supernova subimage to determine whether it was good or not. And so they had 1,000 candidates. So they had about 6 to 8 people every day working for 4 hours looking at these images. It took them about 2 minutes per image to do it. And just by streamlining the user interface, we got it down to 30 seconds. All right, so again, a very simple change, but it dramatically cut the time that it was taking the scientists to process this data. Okay, so this is just what I was talking about before. All right, so I mentioned also the situation awareness problem. I talked about this earlier on a previous slide, so I won't go through this here. Okay, so the context-linked virtual assistant. All right, this was very interesting. So this is imagine this text-based interface with a lot of blinking lights, with text scrolling, and this particular telescope control interface uses curses. All right, this is how this is their legacy software that operates this very expensive multi-million-dollar telescope. All right, and so I said, well, it would be nice if we could rewrite this. Oh, we don't have the budget for that. Okay, so what can we do to help them solve their problem? Well, they don't have any money. They need a solution. So if you'll notice here, we have a chat window in this lower right-hand corner. We augmented chat with a virtual assistant that we call BERT. All right, what BERT does is answer questions that the scientists have while they're dealing with a telescope. Like they might want to know how many exposures can I take before sunrise. Right, but they don't know when sunrise is because they're in France, and they don't really remember when the sunrise is in Hawaii. Okay, so you just type in the chat room, BERT, when is sunrise? And BERT tells you. All right. You can also use BERT to, you can ask any questions about what are good standard stars I can observe. And finally, this was a very popular feature. You can type SOS Greg, right, or the expert, all right? And so Greg is the expert. He knows everything there is to know about operating this telescope. But it's the middle of the night, all you do is type SOS Greg. It sends a text message to him, wakes him up, because he would much rather be awakened. It costs $4,000 a night to operate this telescope. He wants to get good scientific data, all right? So what BERT did, essentially, is it made it very easy to deal with a lot of these problems that could cause, significant amounts of error, right? And because BERT lives in the chat room, it can run, it can run on a Mac, it can run on a PC, it can run on Unix. It's just a very lightweight tool. You don't have to download and install a particular piece of software. One of the things we've learned working with scientists, they don't want to spend an hour downloading a tool, okay? They just won't do it, even if it would save them hours later on. You really have to have a very low barrier to entry. So the advantage here is they don't need to download anything. All right, they just do what they were already doing. It's just like, this lightweight virtual assistant is waiting for them in the chat room, like what they call them sort of a helpful little guy. All right. Also, we have a number of joint papers with astrophysicists. So I want to come back to now what we mentioned in terms of, facilitating scientific insight. So we talked about efficient performance. You really do need to make the computers more efficient, but you also need to make the humans more efficient. And so whenever you're looking at one of these science projects, it makes sense to run an efficiency analysis on how the whole project works, because you can get surprising results from a very low amount of effort, which is quite inexpensive. And this is part of how we can approach this gap between human cognitive capacity and the amount of data that we have to understand. So by doing research in computer science, essentially, we were able to improve the efficiency of the software and the efficiency of the data search for the Supernova Factory. And as I mentioned, we had, in some cases, up to 70% speed up per image, 90% labor savings on the search and scanning. So this was, the reason I put this slide up is there's always a challenge when you talk to physicists or domain scientists. Why would you hire expensive computer scientists rather than, say, one cheap graduate student? Why do you want to hire a team of people with different expertise? And the result is, by having a team, as we have, a Berkeley lab, we were able to really, cut down the operational labor costs of the Supernova Factory in each of these particular tasks. And so somebody once asked me, well, does this mean all the postdocs, got laid off? I said, well, no, the postdocs got to do science. All right, so the result of this ended up being, more publications. So just as a comparison with the data processing improvements, so before we started Sunfall, we were processing about 200 square degrees of sky per night. Afterwards, it was more than tripled. We did this all in the same amount of time, which had to be less than 24 hours. The efficiency, our rate of selecting false positives, actually went up. So even though we had fewer objects scanned by humans per day, that data was of higher quality. So what does this all come out to in the end? I always like to show this graph, although it's really not quite fair. I mean, I joined the project right here, okay, but it wasn't just our software that improved the test. There were many other projects, many other efforts that were going on as well. But what you'll see is over time, this is the rate of, we've now discovered over 1,000 supernovae that have been spectroscopically typed at the Supernova Factory. And so you can see how these flat spots, by the way, we would always stop during the winter because the weather tended to be bad, and you don't want to have expensive telescope time if you can't even open the dome. All right, so you can see how the slope increased over time so that we were more efficient in discovering more supernovae. And just to give you some idea of the impact of this on science, this is the currently available data set of supernovae, all right, that have been studied, spectroscopically. And the yellow bar is in the nearby range. Okay, so see what this shows is if you're looking at looking at the change and expansion of the universe. You see, this bend in the curve is very important. So seeing what's happening at this end of the curve is very critical. And they had about 51, okay? And so what they're saying, so it turns out that 100, this is one subset with the 40 supernovae that we've discovered, but we've actually observed 150. So in other words, just so the 40 new nearby supernovae in this particular range nearly doubles the world sample of the nearby supernovae for cosmology. Right? So this has tremendous impact in the physics world. And these results are going to be presented in January at the American Astronomical Society meeting. Right? So I'd like to encourage you to look into these talks. I mean, you'll probably be hearing about them on the news because they really have made some tremendous discoveries. So this is Greg Aldering's talk that says we have 1,000 supernova discoveries, with almost 400 of them are type 1a. Okay, and so you know, to summarize here, the return on investment. Since I was an entrepreneur, I started a business. I have to look at things in terms of return on investment and benefit. Building, you know, the investment of having computer scientists on this project, building this tool, took about 1.5 years. We had about 5 person years of you know, computer scientist time invested on the project. But it paid for itself in operational costs alone within 1 year. Remember, I had that 5.25 FTE savings before. But much more important than that is the new science discovery that was enabled. That's really the bottom line for science, all right? And you have profits in the commercial world. In science, what you have is publications and science discovery. So to conclude, I want to encourage, you know, students and anybody involved here, consider looking at applied research in computer science. There are a lot of very interesting problems that need, computation is needed in just about every scientific field now. I mean, I don't know of any scientific field where people aren't using computing very heavily, all right? As I said before, I'd like to, if there's any funding people in the room, the single source funding for the interdisciplinary collaborations is very critical. And it's important to be able to leverage previous computer science research, bring in expertise, and from all these different areas in order to successfully produce software for scientific projects. So thank you very much, and I'd like to take questions now.
Excellent talk. We have time for a couple of questions. Is there questions from the remote sites?
Not yet.
Yet? Okay. So in addition to help identify the supernovas, can this powerful computing power be used to do further data analysis for the follow-on work?
Absolutely. I mean, that's part of what's going on right now, is that we need to analyze the spectral data, and this is where, again, machine learning techniques, boosted decision trees, are being very helpful in determining some key cosmological parameters that we've been able to get out of this very rich, you know, data set, because it's a very large supernova data set, and it was observed uniformly. That's really critical in astrophysics, because all these supernovae came from the same telescope, all right, and the same spectrograph. That's really important, because otherwise you can be comparing apples to oranges, and it can be very hard to calibrate the distinctions.
Yeah. Any other questions?
Yes.
I was surprised to hear that the expensive telescopes get sort of directly manipulated by the amateurs. And why would you have, you know, a really trained staff person that plays that instrument like a virtuoso? People just tell them what they want to look at and give them their budget. Says, those 17 shots with those priorities, do the best you can. Since there's a lot of waste on a very expensive equipment, if people, let's see, where do I open the dome now or something?
Yeah, well, okay, so this all has to do with the politics of astrophysics, right, which is a much more difficult problem than solving, you know, building computational algorithms. That's the way they've always done it. They have a telescope operator, but the telescope operator will not, they will just set up they'll set up the equipment, but they will not move it and point it for you. The astronomers themselves have to do it. That's the way they do it. Believe me. All right, this is how it was done. So we're trying to improve things with the computation a little bit at a time, but some things you can't change because in the political realm
More scientific follow-up question.
Yes.
Given the added 4D supernovae that you added on that curve,
yes.
how much more precision did you get in the curve, and how much a better data point did that give you on the acceleration of the expansion of the universe?
Okay, so that was let's see if I can show you the slide. I'm sorry, I don't know this. Okay. So I had a slide here. Let me see if I can find it that shows you There was a graph where, okay, so do you remember the graph that I showed where there was the constraints on the cosmological parameters? If you just look at the Supernova Legacy Survey versus the Supernova Factory? I apologize, this is using a different version of Word than I normally use, so I can't get it to come up. Essentially, it looks like it's about what is it? Maybe about a 70% tighter bound. That's just by looking. Sorry, slow computer. Yes.
I just have a remote question here. Santa Cruz would like you to please talk a little bit about the visualization part of your application.
Okay, so we had, there were many different visualizations that we developed for this particular, so which one in particular did they want? They just, okay, so I'm trying to find this graph here. There it is. Okay, so this is to answer your question, this is the, yeah, okay, so over here you have lambda. Okay, so this is it's omega sub m, which correlates with lambda, and then W0 is a parameter that has to do with whether the universe is flat or not. Now, I'm not a physicist, so I don't know all the details, but essentially these are two parameters that have to do with the cosmological equation of state. And as it is now, we're estimating that, we know that the universe is expanding. We have sort of this large area in there of the parameters. We don't know exactly where it is. And with the Supernova Factory data, which is these 40 ones, we can compress it and get 2 more of these. But exactly what those parameters are, you'd have to ask an astrophysicist.
Okay, so black was before and red then.
Yes, that's correct. That's correct. That's the improvement. So the next question was, what about some of the visualization techniques that we used? Okay, so first of all, okay, so I work in visualization where we often dealt with 3D visualization, very, and this is what I've always enjoyed, is very complex 3-dimensional visualizations to deal with very large amounts of data. What we found in doing studies for the supernova scientists, they didn't need complex visualizations. As a matter of fact, they wanted all their visualizations to be 2-dimensional, all right? So let me see if I can give this is just some of the images that some of the visualizations that we used, okay? And as you can see, they're really quite simple, but this is very effective. This tool in particular, you see there's a number of small visualizations on there that all have to do with the supernova data. And to give you an example of how this was used, when I first started in the group, the typical, what would happen is sometimes there would be some interesting discovery would be made outside. For example, somebody would say, we've discovered this anomalous type of supernova, and it's very interesting, and it has these characteristics. And then somebody in the group meeting that one day said, oh, didn't we study a supernova like that back in May? And in the old days, what they would do is they would assign a grad student or a postdoc, why don't you find this supernova in our data set and come back and give us a report the next week? All right, but as it was, just there in the meeting, somebody flipped open their laptop, brought up the Supernova Warehouse, found the searched for those particular characteristics, found the supernova, said, oh yeah, that's SN 2007 0521-003. We took 20 observations of it. We captured it starting at 10 days before peak, and these are the results. And they put them up on the screen, and they were able to discuss it right there. So this is what makes scientific insight work well. Is you have an idea and you have the data presented clearly immediately. You don't have to wait a week or a month or struggle with it. It's all right there, and that's the benefit of visualization in this particular project.
I wondered whether this data set on supernovae that you collected is able to tell you anything about how the rate of acceleration is changing.
Yes.
Because so far you're able to tell us that the universe is expanding at an accelerating rate,
yes.
But is that accelerating rate exponentially growing, or
right.
is it dying off? Are we going to get to a point where it's accelerating at a decelerating rate and therefore leading to a crunch?
Those are some of the questions that they're going to be addressing in January. Right? The results of some of the results of these tighter bounds on the equation of state. So it's a very interesting time to be a part of this project.
Last question.
My question goes a little bit to the more general academic aspect and work that you spoke about concerning computational work and machine learning. I'm trying to get a sense from you in terms of what the average computer science student learns in programming, and how steep a curve they have to go in terms of learning, or to get to the point where you think they're going to be useful to be able to do any of the kind of work you're thinking about.
That's actually a very good question. This is, I think, a big part of why UC Berkeley has started the CSE program, the focus in computational sciences. Because if people are, people this is, people who are getting degrees in biology now, in physics and astrophysics, it really makes sense to know more about computing than you can pick up by, reading a book on Perl. All right, you need to have training in building larger software frameworks, and it really requires. In terms of how long that takes, I think it takes real training. It takes a couple of years of training at minimum in order to be really useful. Of course, if you're a physicist and you're really smart, you can probably pick it up over time. But it really helps to have the computer scientists then working with you on the collaboration to transfer the knowledge over quickly. Did you have a follow-on question?
In terms of courses or subject areas that you're thinking about more, because the reason being that, I've been on both sides. I've been on the physics side and I've been on the computer science side. And I know that sometimes if you look at computer science and physics, the course development and the course development in computer sciences could be going in very opposite directions, or with different kinds of interests that I know you're not aware on both sides of. So for example, to give you an example, a lot of times, I would just give you an example. It took a while, for example, for physicists to start using Java, whereas computer scientists have started using Java. And so you found, for example, that the curriculums are not the same in terms of using. That's an example.
Right.
Could I suggest
yes.
we break for the formal seminar and we can continue the discussion? This is a really interesting discussion. So let's thank Dr. Aragon again for the wonderful talk today.
Thank you very much.